Hello students, in the last video we actually found the initial velocity for the first compression length, which is 2.90, for the second compression length, and that's going to be 4.04, and then for the third compression length, which is 5.34 meters per second for each one of these values. Now what we want to do is we want to produce a sheet that looks similar to this, and we want to find the spring constant for each one of these positions. Okay, so let's just go ahead and push the plus sign, and after we push the plus sign, let's just call this Hooke's law. Hooke's law dash 2. And so I'm just going to go ahead and go right here, and I'm going to say compression length. I'm going to give that a title. And I should say compression length position or compression length number, but yeah, position will do. I think that's being formal enough. You wrap that. Let's go ahead and center and middle that. Let's expand this so it'll be a little bit legible. And we have compression length 1, 2, and 3. Okay. The next thing that we want to put in here is mass. So we don't, I'm sure that you can do it a different way, but in this case, let's just put mass in. And this is going to be in kilograms. I failed to do this for the last one. Let me go ahead and middle and center this. The compression length is in meters. So we try to stick with the standard. All right. So we have meters, and that's going to be 16. So this, I know we measured the ball. The ball is going to equal to 16 grams, and we need to divide that by 1,000 to get a kilogram. So I'm just going to go ahead and fill and pull that down. All right, the next thing we're going to need is the initial velocity. And if I just go back to my other sheet, yeah, we're just going to grab the initial velocity here for these respective clicks. And that's going to be in meters per second. So let me middle center that. And this is superfluous when you talk about middle and centering it and wrapping it, but it just makes it more readable. Okay, so if you're actually trying to communicate to someone, you definitely want this as legible as possible, as clear as possible, no ambiguity whatsoever. So here we go. I'm just going to go to 1, 2, 3, say equals to, and I'm going to go to the ballistic tool number 1 and select my initial velocity right here using the conservation of momentum, and then I'm just going to hit return. All right, and I'll do that again for ballistic tool number 3, and there's our velocity, return. And one last time for ballistic tool 4, and here's the velocity using the conservation of momentum, and there we go. So now we're going to use the conservation of energy to actually produce this, and all we need to do is we need to find the spring constant. We want to determine whether the spring constant is going to remain constant for each one of these compression lengths. Remember, we formed our hypothesis, and this is the formula: B2, which is just the mass, times C2, which is our velocity, squared, divided by D2, which is the compression length, squared. All right, so let's do that. This is going to be our spring constant. And the spring constant is in kilograms over, I believe, seconds squared. I believe that's what we had. It could be wrong. You guys can do the dimensional analysis to check me off. If I'm wrong, you guys can go ahead and email me. Or I'll probably do it before we get off of this. Let's just check real quick. Not there. We don't need that. Let's go to our sheet here. And the dimensional analysis, yep, we did it right here. right here. And it is kilograms over second squared. Did I move this over? Let me see here. Move that back. So this is going to be equal to, cancel that. This is going to be equal to the mass. Oh, you know what I left off? The compression length. So let me just get rid of that and clear that. So let me insert to the left the compression length. It's the only thing that we left off. Compression length, and we need this to be in meters. Alrighty, so let me just open this up a little bit. Okay, so let's go ahead and acquire that information. This is going to be equal to, and it's on the sheet that we had before. It's right here, so let me move this back. Negative 3.4 centimeters. All right. So this is going to be negative 3.4 centimeters. We need to divide that by 100 to convert it to meters. And then the next one is a negative 4.5 centimeters. And that is just going to be equal to negative 4.5 divided by 100. And the last one is a negative 6.2 centimeters. Negative 6.2 divided by 100. Now we can actually do our spring constant. Spring constant is going to equal to the mass times the initial velocity squared divided by the compression length squared. All right, there we go. We have our spring constant, 116 kilograms per second squared. Now we can just fill that and drag that down. I went a little too far. Got a little too happy. So what you see there is the spring constant is not remaining constant. So if your hypothesis is that the spring constant will remain constant for each one of these compression lengths, you have to reject your, nope, not reject, you have to, your hypothesis fails, okay? So you have to come up with an alternative hypothesis. And what we determined was that the spring constant will be constant over very small displacements, as opposed to these large displacements that we're having. That's pretty much it. So submit this assignment and you will be done.